In this video, we are going to learn about VLSI introduction. Very large scale integration. VLSI is nothing but very large scale integration as a process of creating an integrated circuit by combining thousands of transistors into a single chip. So we all know that before VLSI is introduced, we used transistors in the form of IC, but more number of transistors are integrated in a small chip which we refer it as VLSI. The era of VLSI started in 1970s when complex semiconductor and communication technologies were being developed. Microprocessor, which we normally use in our systems, will be referred as VLSI device. Before the introduction of VLSI technology, most ICs had limited set of functions that they could perform. So because only less number of transistors can be integrated in a single chip before VLSI, obviously the number of functions that they perform will be also less. Different design techniques are there in the VLSI. Hierarchical design approach. In this, we'll have divide and conquer paradigm that will be used to partition a large hardware system into several smaller subsystems. So one big system will be divided into small systems. These subsystems are further partitioned into even smaller ones, and this partition process is repeated until each subsystem can be easily handled. So once we say like a big system is there, we can divide that into smaller and still smaller and still smaller until the design becomes simple of that particular smaller part. This design methodology is known as hierarchical design approach. Top-down approach, bottom-up approach. That are the other two design techniques. So in the case of top-down approach and bottom-up approach, if we see 4-bit adder, if we consider, so 4-bit adder means 4-bit binary parallel adder. So we know that in order to construct 4-bit binary parallel adder, 4 full adders are required, and in turn for every full adder we require 2 half adders and an OR gate. Similarly, for half adder we require XOR and AND gate. So if we come from top to bottom, we say it as a top-down approach, and if we go from bottom to top, we say it as bottom-up approach. Features of hierarchical design. We'll have different steps in this design part of hierarchical method. The first step is modularity. That is, the complete system will be divided into modules. And when we divide them into modules, obviously we need interfaces to integrate them. And in the case of locality, detailed implementation of each module is hidden from outside. So we are not showing the design involved in each module, but we will show how the different modules are integrated to each other. That is how the output of one module will be given as input to the other module. Regularity. Reusability, modules can be reused many times in a design. So what part we need to reuse and how many times we can reuse, all this can be decided in this particular phase. So design abstractions. This is we can say as a steps in the design of VLSI chip. So VLSI chip is designed by the following: the design process or synthesis flow, how we are combining different components and all. So to begin with, a set of requirements, also called specifications, tell what the system should do, how fast it should run, what amount of power dissipation it could have. So whenever you are going to start the system development, we are supposed to get some requirements. That is how the system should perform, that is what operation the system should do, and how fast it should run, that is how much delay we can have in that particular system, and at the end how much of power dissipation it could have. So how much amount of power, whether it could take more power or it should take only less power, everything will be decided in the requirements phase actually. So specifications are often incomplete and subject to be changed later. So here, normally when we talk about the requirements, it is always recurring process. So once we develop something, always like we'll check whether it is meeting the complete requirements or not, and if any changes are there, again we are supposed to recycle that particular thing. So here in this, I am considering the example as design and adder to calculate the sum of two numbers in order to illustrate all these steps of design abstractions. So the various levels involved in the design abstractions are behavioral level, register transfer level, gate level, circuit level and layout level. So these levels I am showing in the form of different system, that is system level. So here we say that behavior level is a system level. Here we say register transfer level as a module level, and gate level, circuit level, and finally device level. So device level also can be called as layout level. So in the case of behavioral level, the very first level, the chip design normally can be done in the form of like a program, software program, which can be normally written in C, Verilog HDL, VHDL. So here VHDL is nothing but basically in Verilog HDL or VHDL, HDL is nothing but hardware description language. So in the case of VHDL, V is nothing but VHSIC, that is very high speed integrated circuit. So it is much more precise than specifications. So normally if I say like adder to, this is the specifications what we are telling, design an adder to calculate the sum of two numbers. So this is nothing but what we say as requirements. So this we are going to show in some pictorial representation in the case of behavioral level. So simulation results of behavioral modeling are used to annotate the specifications of chip design. So as I already told you, pictorial representation will be given. So in order to perform the addition of two numbers, so in the behavioral level, we are supposed to tell how many inputs are there and how many outputs will be there in that particular system. So at this level, only the behavior of the design is verified. That is how it is going to look only will be given in the behavior level, but not how internally it will not be given in the behavioral level. So behavioral level design for a 4-bit adder, if you see, I have given a Verilog code in this case. For adder 4-bit behavior input, we are taking 4 bits as inputs for X and 4 bits as inputs for Y. Input carry will be there, and output will be 4-bit sum and output carry will be there. So what we are telling is basically 9 inputs, that is 4-bit two numbers addend and organ and input carry, finally output sum and carry output. So here we say that behavior will be like C out comma sum equal to X plus Y plus Cn. So when we add X plus Y plus Cn, will be getting the sum and carry out. So the most significant bit will go to C out. Like this we will define the behavioral level design. The next step is register transfer level. So at this level, design is described by a set of Boolean functions. So how we are going to give the in detail design will start from this particular process. So the input and output values of the design on every cycle are exactly known. So as we see that the sum of two binary numbers will take more number of cycles in order to perform its operation. In the behavioral level, we are seeing only at the end of complete operation. In the case of register transfer level, at every cycle we will be knowing what is the output and what is the input. Components used in this level are full adders, decoders, encoders, multiplexers, demultiplexers, resistors, counters and so on. That is MSI circuits will be used in this particular case. At this level, delay and area can be roughly estimated. So based on the requirements, we are supposed to use a particular MSI such that delay is meeting the requirements actually. So register transfer level, RTL is nothing but register transfer level structure for 4-bit adder. So for 4-bit adder, we already seen this particular structure. Module adder underscore 4 underscore bit under RTL. This structure we have seen in the behavioral level, and wires we are telling C1, C2, C3 are required in order to connect the components. So 4 full adders are required, And here one for first full adder, inputs are x0, y0 and cn, outputs are c1 and sum of 0. And second full adder, inputs are x of 1, y of 1 and c1. You can see that output of FA1, that is C1, is coming as an input for FA2 here, and C2 sum of 1 is the outputs of second full adder. For the third full adder, x of 2, y of 2 and C2 are the inputs, C3 and sum of 2 are the outputs. For the fourth full adder, x of 3, y of 3, C3 are the inputs and C out and sum 3 will be the outputs. Like this, one step will be forwarded when compared to the behavior level in the case of RTL structure. So in the pictorial form, if we want to see this 4-bit binary parallel adder, this is nothing but the behavior level, and this is nothing but the RTL level, what we say. So then the gate level. In this level, the design is structure of gates. That is, full adder will be constructed using gates here. Flip-flops, latches, internal structure will be coming out. So at this level, more accurate delay and area can be estimated. So in the case of register transfer level, we'll get the approximate delay because we will not be deciding what are the gates involved in that particular MSI. So here, because we are going to decide the gates also, the delay can be accurately designed. So here switching functions of the design need to be derived. Gate level example of full adder is shown in this case. Normally, full adder can be constructed using 3 input XOR gate and 3 AND gates and 1 OR gate also. And in this form, using 2 XOR gates, 2 AND gates and 1 OR gate also we can construct. This is the reason why I told you that RTL level we can just approximately we can calculate the delay, but in the case of gate level we can just calculate it accurately because all the gates involved in the design can be known. So this is the gate level description if we see in the form of programming language. Here we tell that full adder will have 3 inputs, 2 outputs, and each full adder is having 2 half adders and an OR gate, and each half adder will be having 2 inputs, that is XY and output CS. So what gates are involved in the construction of half adder? XOR, for which S is the output and XY are the inputs. AND gate is used wherein C is the input and XY are the outputs. So if you see, for MSI circuits, first we will give inputs and then outputs, but for the gate level OR gate, if you see here, output is specified first and then inputs. Similarly, XOR gate and AND gate, we are specifying output first and then inputs. This is the gate level description using programming language. The next one is the circuit level. At this level, the design is implemented with transistors. In CMOS technology, the basic gate is an inverting circuit such as NAND gate or NOR gate. So here we are showing the circuit level of a 2-input AND gate. Finally, the layout level. So here the design is to represent the circuit in mask layout layers. So normally the circuit level will be represented in the form of stick diagram also, which will not actually follow the layout design rules. So when we incorporate layout design rules to the stick diagram, we can get the layout design for the complete circuit. So here if you see, this is the stick diagram for a 2-input AND gate at circuit level, and here when we incorporate layout design rules for the stick diagram, we'll have the layout of a 2-input AND gate in this fashion. You can see the similarity between the layout design and the stick diagram here. The references I have taken from this textbook. Thank you.